Hello and welcome back. For this video we'll be discussing exponential functions. There is a PDF available if you'd like to print it out and follow along. An exponential function is a function in the form of y equals a times b to the x power, and you'll notice that the x is actually the exponent in this problem, or we could write it as f of x equals a times b to the x power. Now there are some limitations here. You cannot have a be a 0. If you did, the whole thing would equal 0. And the b value needs to be bigger than 0, meaning it should not be negative. So 0.1, 0.2, anything that's positive but not negative. B should also not be equal to 1, because then you don't really have an exponential function. If I have 1 to the second power, it's equal to 1. 1 to the 200th power, it's still equal to 1. It could be any positive number except for 1. Something about exponential functions is that they are not linear functions. They do not create straight lines. We're going to compare a linear function here to an exponential function. We have both functions written out here. You'll notice in a linear function, if we start with -1 and subtract -4, we get a +3. So each time we go up in the sequence, we're adding 3. Well, in an exponential function, we don't have a common difference. This is called the common difference, or the CD, of a linear function. It's also known as the slope of the line. But if we look at the common difference, let's say between the 2 and the 6, we have a +4, but between the 6 and the 18, we have a +12. It's not the same every time. However, if we take each number, let's say the 6, and divide it by 2, we get a times 3, and the 18 divided by 6, we get a times 3. So we don't have a common difference, but we have a common quotient. So we're multiplying each time by 3 to get bigger in this problem. And you'll also notice that this 3 right here that we're multiplying, the common 3 that we're multiplying, happens to be the base number of our exponent. So in our b value, in our a times b to the x, the common number we multiply here becomes the base number that we're going to be raising our exponent to. The 2 out in front here, we'll figure that out here in a moment, but for right now, if the x value was, let's say, 0, if we input a 0, 3 to the 0 power would give you a 1, and 1 times a would give you the output, or the y-intercept. So that ends up being a 2. So if we know what the 0 power, or the 0 input is for x, we can figure out what the a value is, because it's always the y-intercept. In this case, it's a 2. So for example 1, we're going to write a function rule from the table. So first thing we'll do is check to see, is there a common difference? Well, that would be a +2, and this would be a +4, and this is a +8. So it's not a common difference, so that means it's not linear. So next thing we'll check to see is there a common quotient? So we're going to take 4 and divide it by 2, and we say, okay, well that would be a times 2, and then 8 and divide it by 4, and that's a times 2 also, and we have a times 2, and we have a times 2. So our common quotient, or our common number that we're multiplying by here, always becomes our base number. So we have a b value of 2. In order to find out the a value always occurs when the x is 0. So we look for an x is 0. We have one right here, which means our a value is 8. So a is going to equal 8. So our function can be written as f of x is equal to, and we have a, which is 8, times, and then we have 2 is our base number to the x power. Only the 2 is being affected by the x, not the 8. So if we want to check to see if this is right, we take, let's say, x of 2, and that would be 8 times 2 to the second power. 2 to the second power would give us 4, and 8 times 4 produces a value of 32, which is expected when x equals 2. So we know that this function rule will work. Let's try another one. 9 divided by 3 is times 3, so we got a factor of 3, 27. Divided by 9, I get another 3. 81 over 27 is times 3, and next one is times 3 also. So this becomes our b value, the 3. A value, that occurs whenever x is equal to 0. So our a value is 27. So our function is f of x is equal to 27 times, and our b value is 3 to the x power. Now you could write it like this, 27 times 3 to the x, put our f of x out in front. You don't always need the parentheses, but you probably should have something there to indicate that it's not 273 to the x power, but 3 to the x and then times 27. Now we do run into a little bit of an issue here. For example, 3. We're only given 2 points on the graph, and we are saying that it's an exponential. So how do we go ahead and figure that out? Remember, this is an x value, and this is the output or y value. So here's another x, and here's another y. Now this is a more advanced way of writing it without looking at a table. You notice we don't have any zero power here, so we don't know what the y-intercept is going to be. So what we need to do is something special. So we're going to take our y equals abx, and I'm going to just call this a y, and I'm going to choose one of these to start with. I'm going to start with the bigger one, the bigger y, and put 500 in place of y equals, and I don't know what a is, so I'm going to leave that blank. I don't know what b is, so I'm going to leave that with just a b, but I do know that the x is a power of 3's, so I'm going to put ab to the third power. Then I'm going to draw a fraction bar, and I'm going to do the same thing for this one. So my y value is 20, and that's going to equal, I don't know what a or b is, but on this one the exponent is 1. Now we have to draw back on our rules of divisibility with exponents. So b to the third over b to the first is going to give you b to the second power. Well, a divided by a just drops out of the problem. Then I still have an equal sign. And then 500 divided by 20 is really going to give me 25. So I can solve for b by taking the square root of both sides. So I have b equaling 5. So I know I now have a b value of 5. So this number here has to be a 5. So how do I get the a value? Well, we'll go back and pick one of these numbers. I'm going to choose this one right here because it's smaller. We have a y value of 20. I still don't know what the a value is, but my b value is 5, and of course my exponent was a 1, so 5 to the first power. So that's really 20 equal to 5 times a, because 5 to the first is just 5. Then I divide both sides by 5, and I get an a value of 4. So now I have a b value here, I have an a value here. I can now go ahead and write my function rule. So I'd start off with f of x is equal to, my a value is 4 times, my b value is 5 to the x power. And if you want, you can go ahead and put parentheses around this. Example 4, what is the domain and range? We've gone ahead and shown a graph of the base function here with f of x equaling 2 to the x power. Now domain is all the possible x values. So if we look at this graph, we can see that our x values are going this way and this way, and there appears to be x is going infinitely this way, and even though this is getting steeper and steeper, the further out this way I go, it should still keep going on and on and on. So our domain values should be all real numbers, all real numbers. Now our range though does have sort of a limitation here. As this curve comes down, it gets closer and closer to x, but it doesn't appear to pass the x, which means the y values don't appear to touch 0 or go below 0. On the other side, my y values appear to go infinitely upwards. So in this case, it looks like our range values are all y values greater than 0. So in other words, all positive real numbers. And that kind of makes sense because we're talking about 2 to the x power. So if I put in, let's say, a 3 on there, 2 to the third power, well, that's going to make this thing go up to positive 8. But what if I put 2 to the negative 3 power? So all the negatives are on this side of the graph. 2 to the negative 3. Well, that's really 1 over 2 to the positive 3. And that's really just going to be 1/8. So no matter how small this negative number gets, I'm still going to end up with a positive value, only it's a really tiny positive value. So in the base look of this function, which is 2 to the x power, we're never going to get a negative value for y. The output will never be negative, so we have the range being all values greater than 0. For this one, we're just going to compare. We've got this primary, or let's call it the parent function right here. Y is equal to 2x. And you'll notice that it has a y-intercept of 1. And I did allude to this earlier, that your a value is generally your y-intercept. So this can be rewritten as y equals 1 times 2 to the x. And then right here you can see we have a y-intercept of 1. We'll compare that to the y equals 3 times the 2x. Well, we still have a 2 to the x, which is going to create the same general curve, only now I've got a times 3, or a out in front of 3. And if you look at this 1, 2, 3, we have a y-intercept of positive 3. So that a value in front of our general function, which looks like this, a to the b, a times b to the x, this a value behaves a lot like the y-intercept of our graph. And y-intercept, again, is like saying our starting point. Where does our graph begin, or where do our values begin? Now compare that with the function that's down here with a negative 3. That just makes every output become negative instead of positive. So we have an a value that's negative 3, and you'll notice that it also has a 3, but it goes through the negative instead of positive.